everyone, my name is Angela Dudley and I'm a senior lecturer at the physics department of the University of the Witwatersrand. Together with myself, PhD students Bernice Septon and Isaac Nape, we are going to show you what it is that we do in the Structured Light Lab. So come on, follow us. This is the office area for our postgraduate students. Most of the time spent here involves reviewing current literature in our particular focus areas, planning, designing, and discussing collectively how to approach various experiments and any problems that arise, as well as simulating predicted results before heading into the lab.
So one of the things that you're probably wondering is what is structured light and how do we make this in the lab? So hopefully what I'm about to show you will give you some insight into this. So structured light is just shaping light in all of its degrees of freedom. So if you're looking at the time domain, wavelength, and of particular interest to us is actually looking at the polarization structure, its amplitude and its phase. How we create this structured light in the lab is just based on a very well-known conventional technique known as holography. So how holography works is you would have a reference beam, just your normal laser beam. You illuminate that onto an object, something that you wish to reconstruct, and the interference pattern that you obtain is termed the hologram. Then by running the whole process in reverse and just illuminating the interference pattern with your reference beam, you can then draw the object that you want to obtain. But recently it's now been possible to do this whole process digitally in the lab. So with the development of devices such as what we have over here is just a digital micromirror device, which consists of an array of very tiny mirrors that you are able to tilt and direct your light into multiple directions so that you can change the amplitude of the light. And then another device that we use a lot of is just a spatial light modulator. And that device is just based on electrically controlled birefringence, where you can actually change and alter the phase of your light and consequently then the shape and the intensity of your light.
Hi, welcome to the Quantum Imaging Lab. Come on in. All our experiments start with one very important ingredient. We take a single intense laser beam and we put it through a nonlinear crystal. One photon that we pump the crystal with gets converted into two photons of a different color. The photons emitted in the process must obey the conservation laws like that of momentum and energy. We can then manipulate these properties to do things like the quantum imaging and teleportation. For instance, here we can pass one of the entangled photons through an object and ask the other what object the other photon is seeing. So we can take this photon and use the SLM to structure some type of object and then ask the other photon over here what is it seeing. By looking at the coincidences, we can build up an image of the object by taking many such measurements. Now, as long as we're obeying the laws of conservation, nothing stops us from the two photons that are entangled being different wavelengths. And so what does this mean for us? Well, it means we have the added benefit of perhaps looking at an object with one wavelength while detecting or asking questions in another wavelength, which is perhaps better resolution and has more equipment. And now we can look into practical issues in this field, such as how many photons do we really need in order to create a light when we include intelligence? Or can we extend the dimensionality of teleportation? And even can we structure the pump so that we can tailor the entanglement to the needs of our experiments? Thanks for coming.
Welcome to the Quantum Communications Lab. We also generate photons from nonlinear crystals. The crystals produce photons that are already entangled in their spatial patterns. Cool, right? So to measure these spatial patterns, we would separate the two photons using a 50-50 beam splitter. One photon goes to an SLM allocated for Bob, and another photon goes to another SLM which is allocated for Alice. On each SLM, we encode different spatial patterns. If the photon has the pattern we want, it can be converted into a Gaussian mode and then filtered into a single mode fiber that only accepts the Gaussian. So Alice and Bob would definitely have a way to know what spatial pattern was on the photon. Now, we can do this to both entangled photons and then correlate them. So what can we do with this? Well, we can perform quantum communication tasks like quantum key distribution, QKD, which is a method of generating secret keys or encryption keys. So how does it work? Well, you would have Alice and Bob performing random sequential spatial pattern measurements on each of their photons and keep the correlated or matching signals. So some of the magic signals are then used to generate an encryption key, while the others are used to test if someone was listening in on their session. Once they have the final key, they can then use it to encrypt a message. So there are many other protocols that work in a similar fashion. I hope you guys had fun. Cheers!